So welcome everybody. Just a couple of announcements for the class. First, your first homework is due tomorrow, due to my email inbox by 3 p.m. Please try to do your best to keep it neat and all that sort of stuff. Second announcement is that your first exam for the class takes place 1 week from tomorrow, and it'll take place sort of in the lecture period next Friday. Okay, more details on that a little bit later to come. And one other thing I'll say is that I will probably hold an exam review. So Brian, you've convinced me. Your colleagues can thank you for that. Good job, Brian. Okay. I'll probably release some practice problems probably this weekend sometime for you guys to work on for exam number 1. Okay. Right. So today, what are we going to work on today? Well, first we're going to ask David if his audio has been fixed. So if he responds in the chat and said, yeah, he fixed it, then we all know he fixed it. And if we don't see him say anything in the chat, then we know it's still broken. Okay. So what we're going to do today, it works if you use the browser now. Okay, congratulations. I'm happy that it works. All right. So what we're going to do today is I've gotten a lot of questions on the first homework problem number 3. So I'm going to go over maybe 5 or so minutes on homework problem number 3 from homework 1. And then we'll discuss sort of gears and linkages and the general velocity relationships between gears and linkages, which is going to be helpful for you to work on homework problem number 5, which is the last homework problem in your set. And then at the end of lecture, we'll probably take 25 or so minutes at the end to work through an example problem using velocity relationships for gears and linkages. Okay, so let's dive in really quick and we'll talk about homework problem number 3. I'm going to share my writing pad with you guys. Okay, so here we go. You guys should be able to see my writing pad now. First things first, I'll bring up the homework so that we're all just sort of on board and remember kind of what the homework looked like. All right, so here's the homework. The angular velocity of a gear is a function of time given by omega is 10 minus 2t squared radians per second, where t is in seconds. All right, we're asking you to derive an expression for the angular position and the angular acceleration as functions of time, then determine the total angular displacement, not the angular position, over the time domain 0 to 3 seconds. And I think it's this total angular displacement that's kind of tripping some people up. So let's go ahead and copy some of the information from the problem down here really quick, and then we'll talk about the problem. All right, so generally we were given that the angular velocity vector omega is a function of time, namely that it is 10 minus 2t squared, and this is k hat radians per second. So we're asked for theta as a function of time. That is the angular position of this piece as a function of time. So to do this, or to figure this out, we're going to leverage our kinematic relationships, which we talked about yesterday at the beginning of lecture, and say that we know that the angular velocity is the derivative of the position. All right, it's the first time derivative. Or if we want to rewrite this, we can say that 10 minus 2t squared is equal to d theta dt. Right, so we'll sort of rearrange some things here and go through our separation of variables, which is a technique that you hopefully learned in differential equations. Okay, so we'll rearrange this to write something like d theta. So I'm bringing theta to the left-hand side is going to be 10 minus t squared times dt. Sounds like someone out there's got their microphone unmuted, so please mute the mic. Yeah, please mute the microphone. Thanks. Okay, so d theta, 10 minus 2t squared dt. So this is something we're going to integrate. So we can integrate this guy, and we have to think about what the bounds on our integral is going to be. So here's our integral. We can integrate both sides. And we're told in the problem that the initial position of the initial angular position is 0 at time 0. So the initial angular position is 0 at time 0. So these are the bottom portions of the two limits of our integrals. And because we want a general equation to relate theta to time, we're going to keep the upper portion of our integral bounds as general values. Okay, so this will be theta on the upper end, and this will be t on the upper end for our time integral. All right, so when we execute this, you're going to end up with something like theta as a function of time is going to be 10 t minus 2/3 t cubed. All right, so this is part of the answer of the problem where we've derived a relationship between the angular position theta and time t. Now your next inclination to solve the problem might be to determine what the angular position is at time equals 3 seconds. Okay, so if t equals 3, you find that theta is equal to 12 radians. Okay, yes, the angular position of the piece after 3 seconds is at the position 12 radians. However, that's not the total angular displacement. We need additional information because we don't necessarily know how we got from the position 0 to the position 12. Let me explain. I can sort of use a linear analogy here. Let's say I wanted to move 12 meters to the right. Okay, there are many ways in which I can get there. I can move directly 12 meters to the right. I can move 10 meters to the left, then 12 meters to the right. Or I can move 50 meters to the right and come back 38 meters. All right. The point is that in all of those situations, my total displacement to get to that location was different each time. If I go to 12 directly, my total linear displacement is 12 meters. If I go out to 50 and come back to 12, my total linear displacement is 50 plus 38 or 88 meters. Okay, so the idea is we need to know about the history of our angular motion to understand how much angular displacement we've had in total. So to do that, it's best to plot your function and see what the function looks like over time and what your angular position is over time. Okay, so let's plot theta as a function of time. So this will be a very crude graph. You could probably do this in MATLAB or maybe on your calculator if you want to see what the actual function really looks like. But here we're interested in the domain 0 to 3 seconds. So let's just kind of parse this up. And we know when t is 3 seconds, the value of theta is 12 radians. We also know at the very beginning that our angular position is 0 at time 0. We want to plot what this particular function looks like over time. And if you do this, it will look something like, I'll do my best, something like this. Okay, it's a third order function. So it's going to have some curvature and it'll ultimately look like this. So I agree that after 3 seconds, the angular position is 12 radians. However, for this particular problem, over the duration 0 to 3 seconds, it looks like we went out beyond what was 12 radians. So if this is my threshold of 12 radians, we actually went out beyond 12 radians, and then we came back a certain amount to get to 12. So my total angular displacement is the amount that I went out plus the amount that I came back to get to 12. All right? So total angular displacement is amount I went out plus amount I came back. Ooh, terrible. Okay, so if you want to calculate the total angular displacement in math language, we might say that something like the total angular displacement, if we say that this value here is theta max, then the total angular displacement is the total distance that I went out from 0. So that is sort of this value here, right? I went out to theta max, and then I came back to 12. So the total angular displacement is going out to theta max plus the difference in theta max and 12. So theta max minus 12. This will be in radians. Okay, so that's the general strategy for how to solve that problem. I've had a lot of questions on that problem, so I thought maybe I'd just take 10 or so minutes here to sort of talk through it. Okay, now what you're responsible for still is figuring out what is the value of theta max. Okay, to do that, you might want to think about how you find maximums and minimums of functions in calculus, right? So you know what this particular function is, right? This is a function of time. So you know what that function is. you can take the first derivative of that function, set it equal to 0 to figure out where your minimum and maximum values occur. Here you can figure out at what time your maximum value occurs, plug that time into the original expression for theta to determine what your maximum value of theta will be. All right, so that's the general strategy for solving that particular problem. All right, I'm gonna pause here for maybe 15 seconds and see if anybody has any questions related to that. Got to keep my energy up. Coffee. Whew, a lot of sugar in that one. Okay, so if no one has any questions, we'll continue with the lecture then, and we're going to start talking about the relationships between multi-link components, or the relationship between rigid bodies that share a particular point. Okay, so I'll stop sharing the white pad now, and I'll actually go to the slides for today. Oh, that's not it. You scared of that? I'm scared of that. Okay, so we'll quickly review that if we have general plane motion, which we've been kind of discussing the past couple of lectures, can be thought of as a lot of different points on this particular object, which might all have various velocities. Here we've got an example with two different points, point A and point B, on this mechanics potato that have various velocities. Okay, we can break this up and talk about the relative velocities of these 2 points by thinking of it as a translational component and a fixed axis rotation component. So in this particular example, we've considered the translation of this object with all points having velocity VA. And if we're interested in, let's say, the velocity of B, we're adding to the translational component the additional fixed axis rotation component of point B rotating about the fixed point A. So what results then is we have the translational component of A plus the fixed axis rotation of B about A to give us the total velocity vector VB for this scenario. For us mathematically, we define this using this general relationship, which is the velocity of B is equal to the velocity of A, which is this translational component, plus the angular velocity of the object crossed with the position locating point B from point A. So this is our relative velocity equation, which you will write way too many times for your liking in this class. All right, we did some rigmarole here to show that whether we translate with point A and then rotate about A to get to position, or translate with B and rotate about B to get into position, the mathematics generally work out to be the same. And this led us to the conclusion that if you determine what the angular velocity is on any particular rigid body for one particular point, that you've determined what the angular velocity is for that body everywhere. Okay, and this is true only for the angular velocity, right? We'll see that this is also the case for angular acceleration, but we'll get there a little bit later. So with that information in mind, we looked at this particular example problem where we solve for velocities B and D on this rigid body using things like relative velocity equations and understanding that points A and B are going to be restricted along these sort of like sliders. All right, so this will lead us into some new material that I want to discuss today, and this will help you with homework problem number 5 on your homework, which is the last one for your homework set. And that is talking about how velocity is propagated between multiple rigid bodies that might share a contact point. Okay, so if you thought about how this looked in your statics class, you might have looked at what this was for, like machines and frames and things like that, where if a certain object was pin connected in your statics class, you knew that the force at that pin was equal and opposite. All right, now in this dynamics class, if we have rigid bodies that are in motion, and let's say we determine what the velocity is at one particular point on that rigid body, and that point is in contact or pinned to another structure, then the velocity is shared with those structures at that point. So the idea here is, and I'm going to highlight this image here on the left-hand side, which is sort of like this piston assembly, is that if you analyze, let's say, crank AB, and you determine what the velocity is at point B, you can propagate that velocity knowing that it is the same at point B on this structure as it is on the next link over, which here is link BD. So the velocity here at point B on BD is the same as the velocity here at B on link AB. Okay, so that sort of makes sense. I mean, you can't have two different velocities if this thing is all kind of connected. All right. Same idea goes for something like a rack and pinion, where if you have a rack here R and a pinion gear or a compound gear here, it looks like gear A, B, C, D, that if these two pieces are in contact with each other at, let's say, point B, or here this bottom rack in contact at point C, that the velocity, if you're going to sort of separate these two pieces and look at, let's say, just the rack or just the pinion, that the velocity at point on the pinion is the same as the velocity of point B on the rack. Okay, so if you happen to know what the velocity is of the rack, let's say in some horizontal direction, then you know if you're going to do analysis on the pinion that the velocity at that point is whatever the velocity of the rack is. All right, so this can help you with a little bit more complicated analysis. So with that in mind, let's look at an example problem kind of for the rest of the time here. This example problem looking at propagating velocities between something that we know and something that we want to know. In this particular example, we're going to look at propagating information about link AB to help us determine what the velocity is at point D, which is the velocity of the piston. Okay, so here's this example problem that we have today. Crank AB has a constant clockwise angular velocity of 2000 RPMs. For the crank shown, we want to determine the angular velocity of rod BD and the velocity of piston P. All right, so I'll give you guys maybe 30 seconds to copy that down while I set up the problem here on the writing pad. How's the chat doing? We got any questions? All right. Chat looks good. I'm going to throw it over to the writing pad now. Okay, so here's our example problem from slide number 8 in these lecture notes. And I've just sort of translated the picture over. And I want to just write one additional thing here, and is that we were given crank AB has angular velocity of 2000 RPM. RMP, false. RPM. All right, so let's just lay out what the basic strategy is going to be here, and then we'll execute the problem. All right, so strategy. So the strategy here is we're just going to employ over and over and over our relative velocity relationships. Okay, first we're going to analyze crank AB because we have some information about crank AB, namely that we have the angular velocity of that crank. And then we can propagate, let's say, the information about the velocity at point B to the link BD, which will help us solve for the velocity at point D. So we'll find the velocity at point B with analysis of link AB using the equation that you're going to be sick of by the end of this class, which is that the velocity of B is equal to the velocity of A plus the angular velocity of this crank AB crossed with the position vector locating B from A. Right? So So this is our relative velocity relationship for rigid bodies, which I'm telling you, you're going to be sick of this one. Okay, then once we determine what the velocity at point B is, we're going to move our analysis to the analysis of link BD. So then find our angular velocity of BD and the velocity of point D using analysis of link BD. So again, we'll use our relative velocity equations, something like the velocity of D is the velocity of B plus the angular velocity of link BD crossed with the position vector locating D from B. All right. So again, just writing our relative velocity equations over and over and over. All right. So that's going to be the general strategy. So let's get on with it. So first is link AB. All right. So we'll write our general relative velocity relationship, and that is that the velocity of point B is the velocity of A plus the angular velocity of link AB crossed with the position vector locating B from A. All right, this is our general equation that we're going to be using. Okay, so let's define some things here that we can. First, let's define what is the velocity of A. All right, well, let's go back up to our picture. Here is point A on the structure. It's pretty obvious that point A is not going to be moving. All right, that's a fixed location on our structure. And honestly, what's going to happen here is we're going to reduce ourselves to fixed axis rotation. That's because point A is sort of this fixed point that doesn't move. So if point A is here on sort of this fixed axis, then we can say that the velocity of point A is 0 because it's fixed. All right, so that's helpful. All right. Next, we might want to define the angular velocity vector omega AB. Okay, and this is the angular velocity that we're given in the problem. We're told it's 2,000 RPMs, and we're told that it's clockwise. Okay, so here we have 2,000 RPM clockwise. All right, that's nice, but usually when we're working with angular velocities, we want to talk about it in terms of like radians per second and an actual velocity vector. So we need to convert and write as vector. So mathematically, it's a little bit easier to work in radians per second, and we're going to define the angular velocity as the vector coming out of the page, k hat. Okay, so we have 2,000 RPM, and I'm going to convert to radians per second with a couple of conversions here. First is that we have 2 pi radians by radians for every revolution. And we have 1 minute is 60 seconds. That's terrible. Okay, and we also know that this rotation is in the clockwise direction. So if we go back up to our picture here, I'll get rid of this really quick. The rotation of this is in the clockwise direction, okay? And with our right-hand rule, oh boy, I don't know, is this my right hand or my left hand to you guys? I don't even know. It's my right hand in reality, but I don't know if it's my right hand or left hand to you guys. But anyways, we know that clockwise motion is going to be a negative rotation for us, okay? So this is clockwise motion is going to be negative k hat. Okay, that's the direction that we have for our angular velocity vector. All right, so if that is the case, then we know that this is going to be in negative k hat. All right. So after executing all this conversion and writing our vector appropriately, you end up with negative 209 radians per second in k hat. Okay, and so this is your angular velocity of link AB in terms of some nicer things that we're more mathematically used to working with, radians per second in vector notation. All right. Last thing we need is this position vector locating B from A. Position vector locating B from A. And for this, we're just going to leverage just some trigonometric relationships here. Okay, so we want the position vector locating B from A. That is this position vector here, locating B from A. And notice we're given this angle here of 40 degrees, and we're given the length of this particular link. So that makes our life pretty easy. And we can just say that the position vector locating B from A is simply going to be 3 times the cosine of 40 degrees in I hat plus 3 times the sine of 40 degrees in j hat, and the units here are inches. All right. If we work through the trigonometry here, we'll get that the position vector of B relative to A is going to be 2.3 I hat plus 1.93 j hat. And this is in inches. Okay, so we've defined, sorry, I'll give you guys a second if you're copying this down. All right, so we've defined all of the things here, and we can now solve for the velocity of point B. All right, let's do that. The velocity of B is the velocity of A, which we know is 0, plus the angular velocity of this link AB crossed with the position vector which locates B from A. All right, remember RBA is locating B from A or arriving at B from A, however you want to think about it. All right, so we're ready to punch stuff in now. And we have the velocity of B is equal to our omega AB, which we solved for before, 209 radians per second k hat, crossed with the position vector locating B from A, 2.3 I hat plus 1.93 j hat, and this is in inches. So working this out, doing your cross products accurately, which you've done 100 times now in statics and dynamics and mechanics of materials probably, your velocity at point B is going to be here 403 I hat minus 480 j hat. And this is in inches per second. All right. Let's take a breath here and think about if this answer actually makes sense. All right. So we've got the velocity at point B, 403 I hat, negative 480 j hat. So let's kind of think about with our picture what's actually going on in this problem. All right. So here we are back to our picture. And we know that this guy is rotating about point A in this general direction. Okay, so that's where our angular velocity is going. And with that, it's sort of a fixed axis rotation about this point A. So with fixed axis rotation, you have sort of this circular motion of all points on the object, and specifically that B will follow this sort of circular path around point A. All right. You know from your particle dynamics class that particles will always have velocities tangent to the path which they move. So the velocity of point B should have some direction that looks like this. Okay, this is something that we can sort of check ourselves with, have a little sanity check here. Okay, so looks like if I'm looking at my picture that the velocity of B should have approximately equal components in the positive I and the negative J. Okay, and that's sort of what I have here. I have positive I and negative J, and they're of approximately equal magnitude. Okay, so that's good. That means that the math that we went through here shakes out and sort of collides or corresponds with what we anticipate just sort of by looking at the picture. All right, so far so good. All right. So now we've sort of exhausted all information that we can about what's going on with link AB. Now we have to turn our attention to what's going on with link BD. So let's look now at link BD. And we're going to go through the same sort of analysis, okay? Where we're looking for, ultimately, what's the velocity of point D? It's going to be, again, our relative velocity equations, which is the velocity of B, which is something we know from the previous analysis, plus the angular velocity of this link BD crossed with the position vector which locates D from B. Right? So again, using our relative velocity relationships, you're going to use these over and over and over. Okay? So let's define some of these things. VB we have from before, so that's nice. I'm not even going to really write that here. We know what that is. This angular velocity omega BD, we don't know what it is. It's something we're actually solving for. So let's write it sort of in a general form, and we'll use it as sort of a variable in our equations going forward. So here this is going to be the magnitude of that angular velocity, omega BD, and this will be in k hat. Right? So sort of writing this in its broken down vector form. All right. Next, we have to go through kind of an errand here to determine the position vector of B, D relative to B. So let's go back here and look at our picture. So we want to define the position vector of D relative to B. So we want to define this general vector here. This is the position vector of D relative to B. Okay, well, unfortunately, we're going to have to go through some trigonometry to sort of figure out what this angle beta is. We weren't given that angle beta, so we don't really have information about this position straight away. We do know that this length of this particular member is 8 inches, but we don't know this angle beta. So we need to kind of do some tricks here to figure out our position vector D with respect to B. So let's have a little aside here and let's talk about some of the things that we do know. And that is that we know this particular angle, which is 40 degrees. We know this length, which is 8 inches, and we know this length, which is 3 inches. So if we analyze this in a little bit more depth, you can see here that we have sort of a triangle that makes up this triangle here, which is ADB. And for this particular triangle, we have 2 side lengths, and we have 1 angle in that triangle. So if you sort of remember back to trigonometry, which maybe you took in high school or kind of it's been a while, you should have learned about the law of sines. So to find, we have a little aside here, to find angle beta, which we need to define the position of D relative to B, we need the law of sines. Okay, and a reminder about law of sines, what that is, if you have some general triangle, oh boy, terrible. You have some general triangle that looks like this, and let's label some of these side lengths as like capital A, capital B, and capital C. And you know angles in this triangle. Let's call this angle here little c, this angle here little a, and this angle here little b. Then the law of sines that relates some of the angles in this triangle to the side lengths of the triangle is that the sine of little angle A over capital A is equal to the sine of little angle B over capital B is equal to the sine of angle C over the side length capital C. All right, so this is generally the law of sines. So if we go back to our picture here now and we look, sorry if people are sort of copying this down, sine A on A equals sine B on B equals sine C on C. Here we have this side length 8 inches, and we know the angle opposite of that, which is 40 degrees. Here we have the side length 3 inches, and we're looking for the angle opposite of that, B. So we can leverage the law of sines. Oh, geez. We can leverage the law of sines I don't want to delete the whole thing. There. We can leverage the law of sines to help us find this angle beta. So we need beta. So we can use the fact that the sine of 40 degrees over the length of the triangle opposite of that, which is 8 inches, is equal to the sine of the angle that we're interested in, which is this angle beta, over the length of the triangle opposite of that, which is 3 inches. This will give us that beta approximately equals 14 degrees. Okay, so a small angle, which we can anticipate just sort of by looking at the picture. All right. So then on with the position vector locating D from B. That looks like P, locating D from B. Now we can sort of work our magic here. Since we know that this angle beta is 14 degrees, we can use the length of this link and the angle beta to define things appropriately. And we're arriving at D from B. So we need to move 8 times cosine 14 in the I hat plus 8 sine, sorry, not plus, we're going down in J. So this will be minus 8 times sine 14 J hat. So the position vector locating D from B in this particular example, after we work our math, is 7.76 I hat minus 1.94 J hat. And this is in inches. Okay. So nearing the end here. Finally, we'll come back to velocity of D is the velocity of B plus angular velocity of BD crossed with position vector locating D from B. All right, the velocity of D, I'm going to write as the magnitude of the velocity in I hat. That's because we know, because of the restriction of the piston to move only in the I direction, that the entire magnitude of the velocity will be contained in I hat. So the velocity of D will be in I hat. The velocity of B we found previously with the analysis of link AB, the first link in the problem. And this is going to be 403 I hat minus 480 J hat. This is inches per second. And we're going to add to that our sort of fixed axis portion of this, or the velocity of D relative to B, which is our unknown angular velocity, omega BD in the K hat, crossed with the position vector that locates D from B, which is 7.76 I hat minus 1.94 J hat inches. All right. So let's simplify our cross product a little bit. So if we work our cross product here, you're going to get 7.76 omega BD in J hat plus 1.94 omega BD I hat. Okay, so that's sort of executing the cross product there. All right, so here we have two equations, one in I, one in J, and we have two unknowns, the magnitude of the velocity of D and the angular velocity of link BD. Okay, so this is two equations and two unknowns. So let's just go ahead and solve. We can look at either the I hat or the J hat first. I'm going to opt to look at J hat here first because there's no component of J on the left-hand side of my equation. So let's first look at J hat. And we have 0 on the left-hand side equals negative 480, which is the velocity from translation of B. Here plus 7.76 omega BD. And this, if I just solve, will give me the angular velocity of link BD, which is omega BD, is going to be 61.9. Terrible. Radians per second. Or if we want to write it in vector form, omega BD, 61.9 k hat radians per second. So this is one of the things we were asked to find. And we're reporting here now with proper vector notation. We have both magnitude and direction. So here, 61.9 k hat radians per second. And then the second part of my velocity equation up here, I'll look at I hat. Okay. Oh. So on my left-hand side here, I have the magnitude of the velocity of D. This here will be equal to the portion of translation in I hat and this portion of my motion from fixed axis rotation. Okay, so here this will be 403 I hat plus 1.94, which is here, multiplied by my angular velocity magnitude, which is 61.9 radians per second, or I'll end up with the magnitude here of VD is equal to 403 plus 1.94 times 61.9, which is simply 523 inches per second. Or if we want to report in vector notation, since we know that the velocity of D is contained entirely in the x direction, we'll say that the velocity of D is 523 I hat inches per second. So this tells you what the speed of the piston is at that particular point. Okay, how are we doing? Any questions? I didn't see any questions. All I see when I keep coming back to the chat is David says no sense at all. And it makes me think that my lecture makes no sense at all. But he's actually talking about his technical difficulties. Okay. Makes sense. Thank you. I like seeing makes sense than no sense at all. All right. Well, that's going to be it for lecture today. We'll pick things up talking about acceleration analysis and some shortcuts that you might want to use for velocity analysis tomorrow. Reminder, homework 1 to my mailbox by 3 p.m. tomorrow. And I'll hang out here for a minute if anyone's got any questions. Otherwise, you're free to go. Thanks for coming and listening to me talk to myself. Thanks, guys. Much sense. So, wow. Doge approved. Thanks, guys. Do you think I'll go crazy before the end of the year with all this talking to myself? Probably. You'll just see me slowly deteriorate into madness. Nah, I'll probably be all right. I talk to myself in my head all the time. This just gets it out. I feel like one of those streamers, you know, where people type into the chat and then they talk and yeah, it's just weird. more relevant question is, will you go crazy not being able to talk to me?
I can talk to you right now. I'm right here.
Yeah, there we go. Yeah, that's good. All right. Well, hopefully I don't go too crazy, but maybe. Did you go back to Canada? I know that's where you're like from originally.
I don't live in Canada.
You don't live, yeah. I didn't know if like your parents still live there and you like went back there or what the deal was.
That's the other one, right?
Yeah, that's Jared.
Oh, that's Jared. Yeah, I forgot. I got you guys backwards.
But yeah, he's in Canada. He said they had to self-quarantine themselves for 14 days.
Yeah. So he just like has to be inside for 14
days. Yeah, he like can't really talk to his family either, he said.
He can't talk to his family?
Even like he has to like stay in his room or whatever, or I don't know. Apparently it's more intense than it is here.
Oh. It's probably a good thing. I mean, I still think like people in the US are kind of taking it lightly. It just annoys me. But you know, it is what it is.
Well,
I haven't left my apartment.
Procrastinators.
What's that?
We're notorious procrastinators. We don't do anything unless we have to.
Yeah.
We're reactive, not proactive.
Yeah.
There you go.
Part of the problem is that if you take like really drastic measures, like you just shut everything down and all of a sudden the National Guard starts appearing everywhere and taking everybody's temperature and all that, and the virus doesn't spread, people are going to be like, wow, you were way too aggressive. Like, you didn't need to do all that. The virus didn't even spread. Like, what the hell? And it's like, well, it's because you did all this stuff, right? We're kind of like reacting to everything that happens. And by the time that we react, it's like too late, you know? So
Very
I
true.
just think they need to be more like aggressive with their actions, even more so than what they have been. But
yeah.
I don't make policy, so what do I know?
I don't know. We'll react to it, whatever happens.
Yeah. Well, I'll just be here talking to myself for the next, couple weeks. Hopefully, you guys learn a thing or two.
All right, see you tomorrow.
Yeah, just real quick. How is the speed? Is it too fast? Is it too slow? Like, what do you guys think?
It's a good speed.
I think it's pretty good.
Okay.
Even if it's too fast, like you have it recorded and everything, so people can go back and look.
Yeah, but people aren't gonna do that. Like,
I did it yesterday when I was working on the homework today. So.
Oh, okay. Well, that's good.
I had to do it today.
Yeah. All right. Well, that's good. I'm glad you got your little technical issue there worked out too, David. That was,
Okay, I called the help desk and they're like, "Well, do you want to just try to open it in the web browser?" I was like, "Okay." And then it worked, and I'm like, "But I don't want to use the web browser. I'm going to use Teams app." So I guess I just have to use the web browser from here on out.
Yeah, maybe you can figure it out.
I even deleted Teams and tried to re-download it. I don't know.
And it still didn't work?
Yeah, it's creepy.
There's got to be some like permission thing that is like in your program settings or something. I don't know.
Yeah, I don't know. But yeah, I have senior design meeting tomorrow, and I was like, oh God, if I don't have the ability to do this, I'm so screwed.
Yeah, that's frustrating. Well, anyway, thanks for the feedback. I'll try to keep it going, and hopefully you guys are feeling like you're getting a decent learning experience.
We are in this class for sure.
Oh, yeah.
In this class, how are other classes? Do you have mostly synchronous or asynchronous lectures?
Well, okay, so Dr. Sverdlin, he doesn't understand what's going on at all. Like, one of his things he said was, "Oh, hey, I have a bunch of flash drives with the software that you guys need to use. They're sitting on my porch if you want to come get them up in Mequon." And these kids are like, "Doctor, I live in Illinois. I cannot do it this week, but I could on the weekend." And I'm like, "You got to be kidding me."
Wow, that's ridiculous.
He doesn't do any lectures. It's just like, and his Blackboard's kind of disorganized. So like, I'm literally spending I'm in 5 classes and I'm spending like 40% of my time just trying to figure out what's going on in his class.
Yeah.
It's so disorganized. This class is a breeze though, with not the material, but the
technology gap. Yeah.
The technology.
Yeah, I have an advantage in that I'm young, and when someone tells me like you have to use an electronic writing pad and a laptop to deliver your material online, I'm like, all right, I'll just do it. Like, fine. Yeah. But I think some people are like so afraid of it. Like, I heard horror stories about like Swedish not even like having internet at his house. And, like,
what?
Like having to break down and actually like get internet for his house so he could like deliver lectures from home and stuff. Like,
that's pretty funny.
Yeah.
He got a headset. He got a headset today, so he wasn't just screaming at his computer.
So, I mean, for me, it's nice for me that I'm young and I'm okay with technology, but I know like going to online transition for some people that are old and just don't really know technology that well, man, suspicious.
Yeah, well, then he like assigned like a 10 to 15 page case study paper we have to do instead. It's like, wait, what?
Yeah.
Like more work got added on just because we're from home. I don't know.
Yeah, my philosophy this quarter is I think things should just generally be easier.
Yeah.
I'm gonna like make the exams relatively easy. I'm gonna make the homeworks. You know, the homeworks you have enough time to do what you need to do, so the homeworks will still be a
Yeah.
little bit difficult, but I'm just taking this as like, okay, it's gonna be a little bit easier, and we're just gonna have to deal with some problems. So I don't want the burden to be too high on the work itself. So
Yeah, that's like the whole way it should be done. So I don't
Yeah,
know.
I like the harder homeworks just because it makes you learn the content more and
right,
everything. And it just makes you feel more prepared for whatever exam you're gonna have.
yeah,
So
definitely.
Yeah.
if every homework's super easy, then you're gonna be like, oh, I'm really prepared for this exam. I can do it really fast. And then the exam hits you and you have no idea what's going on. So
Right. Yeah, that's always
Yeah.
my philosophy. Is I like to try to make the homework and the review problems harder than what the exam will be.
Yeah.
Right.
Are you still doing the 80% of points in one problem?
Yeah.
Yeah.
I mean, it's hard for me to give feedback on every problem.
Oh no, that'd be awful. Yeah, the way the way that what's his name did it. Dr. Farrow, we had to spend a whole lecture like grading our own